Hello everyone, welcome back. Today we're carrying on with our grade 12 physical sciences paper 2 from November 2021. We're looking at question 6. Questions 1 through 5 have been done in previous videos, so if you want to see those, check those out. They are in separate videos. Question 6 out of 18 marks, and as I always say, we have 180 minutes for this exam with 150 marks. So for an 18 mark question, you probably want to spend around 20 to 25 minutes max on this question. Okay, so it's always good before you start the question to just have an idea of how much time you're going to allocate to it. And if you see yourself going over 25 minutes on this question, it would be a good idea to just leave it, carry on, and then circle back once you've finished everything else, because you really just want to pick up the low-hanging fruit. Like, just make sure you get all the really easy marks. Like, when I say easy marks, like, I mean all the defined questions. That's just free 2 marks. Yeah, a lot of the 1 mark questions tend to be easy, low-hanging marks. Something like this big 8 mark question here, if you're struggling with it and you're not getting to the final answer, you can obviously just leave some space in your answer booklet and then carry on to the other questions to make sure you get these easier marks, and then circle back to this one after you've made sure you've got the most out of the entire question paper. It's just good exam technique, because you don't wanna spend a lot of time on an 8 mark question and then run out of time and not finish the exam when there were a lot of easier marks that were probably altogether worth more than 8. Yeah, and unfortunately a mark is a mark. Yeah, so even if a question is very difficult, a mark is a mark. So you won't get extra marks for solving all the difficult questions and leaving the easier ones unanswered. So it's just good practice to make sure you get all the easy marks, the low-hanging fruit, and then circle back to anything that was troubling you. Okay. Anyways, I always like to talk a little bit about exam technique before we start a question. Yeah, just it's good practice, something good to have in the back of your mind. Of course, you can apply it not just to physical sciences, but any exam really, especially maths. It's easy to spend a lot of time on certain questions if you're not sure what to do and you're trying a whole bunch of different things. But okay, enough about that. Let's get into the actual question. Consider the balanced equation below for a hypothetical reaction that takes place in a sealed 2 decimeter cubed container. Okay, 2 decimeter at 300 Kelvin. Okay, and it's sealed. So, okay. Yeah, I guess this is pertinent. The fact that it's sealed, definitely sort of pertinent. Okay, so they give us the reaction 2p plus q2 gives 2pq. Okay. Yeah, okay. Define the term chemical equilibrium. So as I always say with definitions, you can phrase it in your own way, but you just have to have some keywords as part of your definition. And here an example answer would be the stage in a chemical reaction when the rate of the forward reaction equals the rate of the reverse reaction. So that's acceptable. You could also say concentration of reactants and products remain constant. So either of those 2 definitions. The important part is just saying that, okay, the rate of forward reaction equals the rate of reverse reaction. That somehow has to be paraphrased or included in your answer somewhere for you to get the 2 marks. Okay. The amount of each substance present in the equilibrium mixture at 300 Kelvin is shown in the table below. Okay, so they give us some concentrations. Well, okay, not concentrations, but we can calculate the concentration because we know that the container is 2dm3. So we can calculate concentrations with this and this both in mind. The temperature of the container is now increased, okay, to 350 Kelvin. What new equilibrium is established? When a new equilibrium is established, it is found that 1.25 moles of P is present in the container. So basically, with our new equilibrium, this shifts to 1.2. Okay. Yeah. Is the heat of the reaction positive or negative? Okay. So here we have to apply Le Chatelier's principle. We can see that at a lower temperature, there was less of P. Okay. So we can see that at 300 Kelvin, okay, P equaled 0.8. And then at 350 Kelvin, P equaled 1.2 moles. So at higher temperatures, it seems that the equilibrium shifts this way and favors the reverse reaction. So that tells us that our forward reaction is probably exothermic. Yeah. So that means it gives out heat. That means it's negative. Yeah. So the heat of reaction is negative. Yeah. I hope we can see that. Use Le Chatelier's principle to explain. Okay, so I've already explained. But of course, this is a 3-mark question. So let's put it into a bullet point form that's easy to understand. Okay. So an increase in temperature favors an endothermic reaction. Okay. The reverse reaction is favored, as we saw, as there's more P. Okay. Therefore, the forward reaction must be the opposite, so it's exothermic. Okay. So you could say it in the reverse order. So you could say a decrease in temperature favors exothermic, and therefore the forward reaction is exothermic. Therefore, reverse reaction is endothermic. So you could like look at it from either viewpoint, but yeah, those are just the 3 points you gotta mention. You gotta talk about the temperature and whether it's favored endothermic or exothermic, and then conclude whether the forward or the reverse, which is which, endothermic or exothermic, and then that explains why the reverse is favored when the temperature increases. Okay, so these are 3 marks really. As long as you understand Le Chatelier's principle, that's an easy 4 marks already. With the definition of equilibrium, that's an easy 2 marks. So this is what I talk about when I say low-hanging fruit. You don't really have to think much about these questions, and we're already like 6 marks out of 18, yeah, which is really good. Of course, now they throw in a bit of a calculation question, which can be harder. Calculate the equilibrium constant at 350 Kelvin. Okay. So usually for this type of question, it's best to make a table. Okay, so we can start with our initial, change, and equilibrium concentrations. Okay, now what's important is that here they give us amount, yeah, not concentrations. But when you're calculating an equilibrium constant, you have to use concentrations, not mole amount. Okay, it has to be concentrations. So we need to convert all the numbers they've given us into concentrations. So let me just grab my calculator. Okay, so for each, let's say P, I should have given myself more space, Q2 and PQ, okay? So for P initially we had 0.8 moles in a 2 decimeter container. So we'll just take it as 2. This gives us 0.4, okay? And then for Q2, same thing, because it was also 0.8, and then 3.2. Okay, which gives us 1.6. Okay. And then at equilibrium, P is 1.2. Okay, this is at equilibrium. So if P is 1.2, so we can say 1.2 divided by 2, this gives us 0.6 at equilibrium. Here the change is plus 0.2. Okay. And what we can see here is that P and Q are related by 2. So whatever happens to P, half of that will happen to Q. Okay. So here the change would be 0.1, and this should be 0.5. And then P and PQ are in a molar ratio of 1:1. So here the change should be minus 0.2, and this should be 1.4. Okay. Does this make sense? Does this make sense? So a good way to check if what you're doing makes sense. What was the change? Oh, did I do this correctly? 1.2, so the change is 0.4 divided by 2. No, I did. Okay. Equilibrium concentrations. Yes, this is correct. Okay. Good. Okay. So now we just plug it into our equation. So equilibrium constant equals products. So PQ. Of course, this is to the power 2 over reactants. So P. Okay, wait, let me just write it first, then I'll plug in the numbers. So P was 0.6 to the power 2 versus 0.5, yeah? Okay, so what I'm seeing here is you can do it both ways. I mean, maybe technically we were supposed to do it in the reverse reaction and then take the reciprocal, but doing it this way is a lot more straightforward. Okay, I meant to write the reactants first before putting in the numbers, but I put in the numbers in the bottom already, so we'll just plug in the numbers, and then this gives us an answer of about 10.89. Yeah. Okay. And that's good for 8 marks. Can you believe it? This actually is a very simple question. Honestly. So I'd imagine you'd get some marks from this table for figuring out like the correct change, the correct equilibrium concentrations, also for converting moles to concentration. And then you'd get some marks probably for the calculation of the equilibrium constant and for the right answer. Yeah. You definitely, I see that they award a mark for writing the equilibrium expression first before plugging in the numbers. So definitely don't do what I did where you just plug in the numbers straight away. You definitely want to write out, let me do it now. Let me not be lazy. You definitely want to write this out first. You will definitely get a mark for writing this first before plugging in the numbers and calculating the actual value. So you'd get something like 3 marks for this, and then you'd get some more marks for like calculating all of these numbers correctly and the change. Yeah, I think, yeah, something like that. And then for converting everything to concentration from moles. So definitely don't skip any steps. You might even want to show some calculations of how you like converted this. So just saying, 0.8 divided by 2 to get 0.4, yeah? You might just want to show that and say that's how you got this. You could get like some half marks for that in case you make a mistake and don't end up with the right answer. So definitely good to show all your work for something like this. But yeah. It's actually, yeah, easy 8 marks. I thought it would have been a more convoluted question, but rather straightforward. Okay, how will the equilibrium constant calculated in question 623 be affected when the volume of the container is decreased at constant pressure? Okay. So again, Le Chatelier's principle. So we got to think about it. So if pressure decreases, if volume decreases, and it's at constant temperature, so we don't have to think about temperature, because usually a decrease in volume is associated with an increase in pressure and an increase in temperature. And you can see that from the gas equation, Van der Waals gas equation. Not sure if you've been taught this, but definitely if volume decreases, then pressure increases and temperature increases. But anyways, they're telling us temperature stays the same. So the only thing that we have to worry about is an increase in pressure, yeah? Okay, so pressure increases. So what does that mean? So if pressure increases, the equilibrium will shift to favor a decrease in pressure, which means less molecules of gas. Yeah, and that's definitely the right hand side of the equation. Here there's 2 moles of gas, and the side there's 3 because there's 2 from P and 1 from Q. So there's 3 moles of gas the side, and the side there's 2. So if there's an increase in pressure, the system will try to decrease the pressure, and it'll shift the equilibrium to the right. Yeah, so that's all you have to say for that question. Yeah. How will the equilibrium so they want us to relate that in terms of the equilibrium okay, so if there's a shift to the right, that means the equilibrium constant will increase. Because if you look at this equation here, if the concentration of PQ increases and the concentration of Q and P decrease, the value of Kc will increase. So it'll be a bigger number than 10. It might be like 12 or 14 or something. So you can see that, and then, yeah, here you just say increases. and that's an easy 2 marks. Okay. Let's move on. More Q gas is now added to the reaction mixture at constant temperature. How will each of the following be affected? The yield of PQ. Okay, so there's more Q gas. Yeah, more Q gas. So if there's more reactant, it's definitely going to favor the forward reaction, so there'll be more 2PQ. So the yield of PQ will simply increase. Okay. The number of moles of P. Yeah, definitely decrease, yeah. Because we're forming more PQ, so P will get used up. Okay, I just want to come back to this question 624. Because in the memo, it says the answer actually remains the same, and this doesn't make sense to me. It says only temperature can change Kc. Temperature remains constant. So Kc remains the same. Honestly, I guess what this question, okay, so I guess the answer, the reasoning I gave, trust me, this reasoning is correct. But I guess the way the memo wants you to think is, okay, so they say, okay, it remains the same, that's the answer, and it's because T doesn't change. Yeah, that's the reason. So basically what they're on about is that, so there's two equilibrium constants. There's Kc and Kp, and strictly speaking, they're not the same thing. So Kp is a function of pressure, and Kc is a function of concentration. And technically, they are saying that temperature is the only thing that can affect Kc, and not changes in pressure. Changes in pressure, if we were calculating Kp in terms of partial pressures, then pressure would affect Kp. And I guess that's the logic they want you to use to arrive at this answer. But I'm telling you, technically that's not correct. Yeah, that's not correct, because a change in pressure would affect the concentrations of the reactants and products, as there would be a shift in equilibrium. And that shift in equilibrium, which changes the concentrations, would affect Kc. But I guess maybe that's thinking too deeply about it. They just want you to think in terms of Kc and Kp and how pressure shouldn't affect Kc. Yeah. I guess that's what they want from us, but technically it's not correct. But okay, in order to get through this exam, you would definitely have to just use this reasoning for these types of questions to get the 2 marks. Yeah, and then of course, yeah, these last 2 are correct for 1 mark, and that's good for 18 marks. I guess, yeah, if you had done the question how I did it, you'd only get 16 out of 18, because I got 6 to 4 wrong. But yeah, really weird. Okay, anyways, I hope this has been helpful, and that concludes question 6.